Welcome to the lesson on section 8.7, Approximate Integration. In this lesson, you'll get a quick review of using right or left endpoint rectangles or midpoint rectangles to approximate the area under a curve. And we'll also look at two other methods called the trapezoidal rule and Simpson's rule. It should be noted that Simpson's rule is not a required topic for the AP Calculus exam administered by the College Board. Many of the techniques you've learned in this course involved both exact and approximate methods. Some of our approximate methods include using tables to find limits and using slope of a secant line to estimate the slope of a tangent line. The square root of cosine x squared plus 2, shown here, is an example of a function for which we cannot find an antiderivative. Thus, the only way we can evaluate this definite integral is by using approximation methods. Earlier in the course, we used approximating rectangles for this purpose. In this lesson, we'll look at two alternative methods that may often result in a more accurate estimate. Instead of using rectangles to estimate the area under a curve, we can use trapezoids. Here's what four approximating trapezoids might look like under this curve. Notice that the parallel sides, or bases, of each trapezoid are actually the lengths we would have considered to be the heights of approximating rectangles. So the height between the bases of each trapezoid is what was considered to be the base of each rectangle. In this case, I've drawn four trapezoids from x equals 0 to x equals 2. So the height between each trapezoid's bases is 1/2. The formula for the area of a trapezoid is 1/2 times the sum of the bases times the height. So the first trapezoid on the left has bases f of 0 and f of 1/2, and the height h between them is 1/2, giving it the area f of 0 plus f of 1/2 times 1/2 divided by 2. The second trapezoid has bases at f of 1/2 and f of 1. The third has bases f of 1 and f of 3/2, and the fourth has bases f of 3/2 and f of 2. We've got some like terms that can be combined in that area expression we just found. The height of each trapezoid was the same, so we can factor that out of the expression. The first two trapezoids shared f of 1/2 as a base. The second and third trapezoids shared f of 1 as a base, and the last two trapezoids shared f of 3/2 as a base. So let's collect these together. The area of those four trapezoids can be expressed as 1/2 divided by 2 times f of 0 plus 2 times f of 1/2 plus 2 times f of 1 plus 2 times f of 3/2 plus f of 2. So by the trapezoidal rule, the area under the curve y equals f of x from x equals a to x equals b can be approximated by h over 2 times the sum of y0 plus 2y1 plus 2y2 and so on up to 2yn minus 1 plus yn. H is the height of each trapezoid, or really the delta x, and the y values are the parallel bases of each trapezoid. Instead of rectangles or trapezoids, Simpson's rule uses the area under parabolas to approximate the area under a curve. Here's what the formula looks like, but of course we'll take a look at a derivation before we use it. Don't worry about copying it down just yet. I'll show this formula again after we derive it. Here's the derivation of the formula for Simpson's rule. Instead of breaking up the area under a curve into areas of rectangles or trapezoids, imagine dividing the curve itself up into pieces of parabolas connected to each other. Each of these parabolas spans two intervals, so the number of intervals n must be an even number. Let's stick with calling the width of each interval h, as we did for approximating rectangles and for approximating trapezoids. Here's a graph showing a sample parabola. Notice that the piece of the parabola shown has a width of 2h, so it spans two intervals of length h. The area under this parabola can be described as the integral of x equals negative h to x equals h of ax squared plus bx plus c, where y equals ax squared plus bx plus c is the equation of the parabola. Integrating, I get ax to the third over 3 plus bx squared over 2 plus cx evaluated from negative h to h. Then plug in the h and negative h and combine like terms. If I factor out an h and a 1/3, I get h over 3 times 2ah squared plus 6c. This is an expression for the area under the parabola in terms of a, b, c, and h. Next, I'll find values for the coefficients a, b, and c in terms of h. First, I'll substitute the coordinates of the points p0, p1, and p2 into the equation of the parabola for x and y, giving me a system of 3 equations. Adding the equations that use the points p0 and p2 results in y0 plus y2 equals 2ah squared plus 2c. And multiplying the equation that used the point p1 by 4 gives me 4y1 equals 4c. If I add these two new equations together, I get y0 plus 4y1 plus y2 equals 2ah squared plus 6c. That may seem random, but it's not. Remember that on the last slide we found the area under this parabola to be h over 3 times 2ah squared plus 6c. So putting those two results together, I can substitute y0 plus 4y1 plus y2 in place of 2ah squared plus 6c. This is an expression for the area under the parabola shown in the graph in terms of the y's. If the curve continued to the right, the next parabola would connect to this one at the point p2 and also pass through points p3 and p4 with y coordinates y3 and y4. Applying the same area formula, the area under this next parabola would be h over 3 times y2 plus 4y3 plus y4. And the area under the next parabola could be expressed as h over 3 times y4 plus 4y5 plus y6, and so on. Adding those areas together and taking out a common factor of h over 3, I get this. There are some like terms I can add together because one endpoint of each parabola is a common endpoint with the next parabola. I get h over 3 times an expression involving the y coordinates of the points on the parabolas. Notice that the first and last y values have a coefficient of 1. The second and second to last y values have a coefficient of 4. This would be true no matter how many parabolas we're splitting the curve into. Then the coefficients alternate from 2 to 4 in between those. To help you remember this formula, remember that y0, y1, and y2 all belong to the first parabola. The reason that y2 has a coefficient of 2 is that the second parabola contains y2, y3, and y4. So as promised, here's our formula for Simpson's rule again. To use the formula, you won't have to think about parabolas or even that each parabola spans 2 intervals anymore. You just need to know about the parabolas to understand why the formula works. You'll find that if you try to use this formula with an odd number of intervals, you won't end up with a 4 as the second to last coefficient, so that shouldn't seem right to you anyway. Our book typically uses a capital S with a subscript to indicate a sum using Simpson's rule, where the subscript indicates the number of intervals we're using. In this sample graph, S4 would indicate that we're using Simpson's rule with the area broken up into 4 intervals. The y values we use in the formula would be the same as the y values we'd use for 4 rectangles or 4 trapezoids. There would technically be 2 parabolas covering these 4 intervals, but you really don't need to know that in order to use this formula, as you'll see in the next example. In theory, if we could divide the curve up into many parabolas and sum up the areas under them, this method could be very accurate. In this example, I'm bringing back the definite integral I showed you at the beginning of this lesson, the integral from 0 to 2 of the square root of cosine of x squared plus 2. Earlier I mentioned that we won't have any rules for finding the antiderivative of this function, so we'd have to use approximation methods to evaluate instead. I'm going to show all the different approximation methods you've learned so far: right endpoint and left endpoint rectangles, the midpoint approximation, which also uses rectangles, trapezoids, and Simpson's rule. Usually our directions will indicate how many intervals we need to use. Since I left that out, let's agree to use 4 intervals here. If I break the area from x equals 0 to x equals 2 into 4 equal intervals, I'll have partitions at x equals 0, 1/2, 1, 1.5, and 2. Right endpoint rectangles would intersect the curve at x equals 1/2, 1, 1.5, and 2. So base times the sum of the heights for each rectangle would come out to be 1/2 times f of 0.5 plus f of 1 plus f of 1.5 plus f of 2. Left endpoint rectangles would intersect the curve at 0, 0.5, 1, and 1.5. So this is what our left endpoint approximation would look like. Midpoint approximating rectangles would intersect the curve at the midpoint between the intervals marked in the diagram. So we would use 0.25, 0.75, 1.25, and 1.75 to find our heights. Let's move on to our trapezoidal approximation. Remember that our formula is h over 2 times y0 plus 2 times y1 plus 2 times y2 and so on up to the y value at the end of the interval. Notice that, unlike the rectangle approximation methods, the trapezoidal rule uses the y values at the very beginning and at the very end of the interval. So in this particular example, f of 0 and f of 2 will both be involved in our area approximation. Also remember that we consider the height h of each trapezoid to be the width of the interval, the part that lies on the x-axis, so h is 1/2. The parallel bases of the trapezoid are the parts that we consider to be the heights of the rectangles, and the 2's that appear as coefficients in the formulas are there because each trapezoid shares a base where they meet. To use the rest of the formula, we just use every y value that lies on an interval partition. So we have f of 0 plus 2f of 0.5 plus 2f of 1 plus 2f of 1.5 plus f of 2. Whatever this evaluates to be would be our trapezoidal approximation using 4 intervals, or T4. Here's our Simpson's rule formula again. For 4 intervals, we'll still use the same partitions as we did for all of the other approximations, and h has the same value as it did when we applied the trapezoidal rule, 1/2. We also use the same function values as we did for the trapezoidal rule, just that the coefficients are different. So the first and last coefficients are 1's, the second and second to last coefficients are 4's, and everything else alternates between 2's and 4's in between. Let's do one more example, using our 2 new rules to approximate the value of the integral from 0 to 4 of the square root of 1 plus the square root of x. n equals 8 means that we'll use 8 intervals. If we break the interval from 0 to 4 into 8 equal intervals, each interval will have a width of 1/2. So for both formulas, we'll use h equals 1/2. The x-coordinates at each partition will be 0, 1/2, 1, and so on up to 4. T8, the trapezoidal approximation using 8 intervals, will be 1/2 over 2, and the sum of the function values will have 1's as the first and last coefficients, and 2's as all the other coefficients in between. For the Simpson's rule approximation, h is still 1/2, but this formula has a 3 under the h instead of a 2. In the parentheses, we'll still begin and end with coefficients of 1. Working into the middle, the next coefficients on both sides will be 4's. Then the rest of the coefficients alternate between 2's and 4's in between. This concludes the lesson on section 8.7, Approximate Integration.